Hi, and we're going to talk about solving systems of equations using the graph. So far we've introduced our linear functions, which is just some straight line going either in a positive or negative slopes, and then our quadratics. The quadratics, they make a parabola, so they're going to give you something like this or something like this. And what we're going to do is we're going to interpret the intersections of them. So finding when they're simultaneously linked is pretty much how you do this. So you take a graph and you'll notice that there's intersection points. So these have the exact same value over here and then again over here. So just by looking at the infinite set of solutions that we have on our graph, or in this finite window anyway, we can recognize that it's going to cross once and twice. And understanding the parent function of a quadratic and a linear, we know that if we can see those two intersections, those are going to be the only two intersections that it has. So we could have something like that. We could actually match our quadratics and quadratics. And same thing, knowing the shape, you can know that it's going to cross once and twice, just based on the shape. You know that this isn't going to curl back around and this is going to magically curl back around and there's going to be a third time. So even in this tiny little window, we can actually recognize the two solutions to this set. Other possibilities, so if we have quadratics that don't link, that means there is no solution to the set of equations. Yeah, there's a lot of solutions for this one and there's an infinite set of solutions for this one, but there's actually no solutions that work for 1 and 2 at the same exact time. So from your homework, number 2, we have this equation and you see it, you notice it's in y equals form, you grab your graphing tool out, you plug it in and it looks something like this. Tendency is, oh wow, this is easier than it looks. I had this complicated system of equation. Answer, x equals 0, y equals 2. Oh no, wait, that's backwards. X equals 2, y equals 0. And you'd be tempted to be done. Now, herein lies the problem with that. If you take a closer look, you're going to notice that the only solutions that we could see explicitly, yeah, 2, 0 was a solution, but if you get real close, you're going to understand that there's going to be a second solution. So with our graphing software, it's actually pretty easy to see that second intersection at 2.25 and 0.0625. That's something we can see visually with this. However, with your graphing calculator, finding that intersection point might not be as explicit. So that's why we're having our algebraic versions of finding this. Identifying this on your graphing calculator is actually pretty difficult. More difficult, in fact, than using algebraic methods of solving. So just be careful. The graphing tool is more likely a better of a checking point than a way to find the actual solutions. Now, using graphing software, it's probably going to be one of your favorite methods because you just got to look at the graph and see when the two things are equal. And using Desmos, they'll identify the intersection points for you. Just by highlighting it, you can find your solutions. So if we're coming across the type of a problem where we have our answers and we can see them nice and visually, where, hey, there's the solution. Oops. There's the solution. And there's its counterpart. I can see that. All right, -1, -4, 5, 6, 7. +2, -7. And those are my two solutions. Or here I can easily see that they're never going to cross and there's going to be no solution. Other than that, I would probably rely on using the algebraic ways.